Hello, I'm Richard with EV4U, and this is our third episode in our series, A Beginner's Guide to DIY Off-Grid Power. Now, if you remember, in our first episode, we talked about how to determine your power requirements. You want to run certain items, and we discussed how to figure out what load those represent. How to figure out the watt-hour requirements that we're going to need to power whatever we want to power. And in the second episode, we talked about the battery storage required to power those items for a day, multiple days, a week, that type of thing. So basically it was the amount of energy over time. It's very simple to figure out. We showed you how to figure it out if they provided the power requirements on the appliance itself, and if they didn't, if they provided you the current draw, we could still figure out the power requirements. So next, we determined what our loads are. We determined on how to meet those loads with the battery pack, and now we got to talk about how to maintain that battery pack, how to charge or recharge the battery pack. And so we're going to focus basically on one method at this time, but we're going to introduce a few others just as options out there. But we can go over some of these others in a future video if there's any request to do so. But one way you can recharge your battery pack is with a charger. Okay, and so depending on what your battery pack voltage is, you'll need the appropriate charger. For instance, in my case, I have an inverter that has a built-in charger, and that charger puts out 75 amps, and that's what will recharge my battery pack if I'm plugged in to the grid or if I'm using a generator. So the generator would provide power to my grid input, to my trailer, and then from there my charger would charge the battery pack. Now, whether you have an off-grid cabin, an RV, or whatever, it's going to be similar. You're going to have, the generator's not going to charge the batteries directly in most cases. It's going to go through a charger. So that's one way. A wind turbine is another option, probably not a real popular one. Hydro, another. This is the greatest option. The beauty of hydro versus solar or a wind turbine is that a Pelton wheel, if you've got a stream or a creek that has enough flow and enough fall that you can run a little hydro generator, they run 24/7. Unlike the wind, it doesn't always blow 24/7, and you don't have solar definitely 24/7. So if you've got it, that's great. Not good for mobile applications, obviously, but if you had an off-grid cabin or something, man, that's to me, that's the dream come true. And then, of course, there's solar, and that's what we're going to talk about mostly today. And then, of course, there's plugging into the grid. And if you have a factory-produced RV, most of those have a converter that's part of the setup. And so what happens is whenever you're plugged into the grid, or if you're plugged into a generator, this converter is taking that AC and converting it to DC, and it's charging your house batteries. And another way that's grown in popularity in recent years is a DC to DC converter. The DC to DC converter typically is taking the input from your starting battery and alternator setup and then charging your house battery with it. And so it's basically intermediary between those two. It allows which was especially an issue with lithium batteries because of their low internal resistance, like we talked about in the last video. They can accept a charge much easier. And so they created a greater demand on vehicle alternators. So the DC to DC converter kind of acts as a regulator in that case and keeps the lithium battery pack from putting too much demand on the alternator. In the old days with lead acid, instead of a DC to DC converter, they used what was called a battery isolator. What the battery isolator did was it allowed you, when you started your vehicle, it would allow the starting battery to be recharged, which happens very quickly if the car starts like it should. And then after that, it would charge your house battery. But it would not, let the house battery discharge the starting battery. That's why they called it an isolator. And so those are very common. I used those for decades. And so those are the main ways that you're going to recharge your battery pack. So today, probably the most common way, so the one that we're going to focus on today, is solar. And so what do you need to recharge your battery pack using solar? Well, you're going to need the solar panels, of course, and you're going to need a solar charge controller. And there's two main types. And I'm thinking down the road I may do a video showing you some side-by-side comparisons of using the two main types of solar charge controllers, pulse width modulation and the MPPT and maximum power point. So anyway, this is the one that I recommend, is the MPPT. But like I said, in a future video, if we could show the two side by side, you could see the side by side comparison of the two and why we recommend the one over the other. Another thing I wanted to do is we'll do a solar panel example demonstration where we have like 4 solar panels, and we'll show them what it's like if you have them wired in series versus if you have them wired in parallel versus wired in a series parallel joint configuration. And so we can talk about the pluses and minuses of those things. Today we're not going to have that physical example. I'm just going to tell you about it. And then, how many solar panels do you need? And then how long is it going to take to recharge? These will be some of the things we talk about. We'll hit about, the big picture, powering your DC loads. Typically lights, water pump, heater fans if you have a central propane heat setup. And then you have your AC loads, which are things such as, could be air conditioning. 12-volt air conditioning units are becoming more popular, or DC in general. But in my case, my hot water heater, or my water heater, is AC. My induction cooktop, that's AC. The microwave oven, that's AC. So those are examples of AC loads. Like I said, DC loads, your laptop, your phone, charging those items, or they could be AC also, depending on the charger you're using. But typically, like I said, the water pump and lights and fans, those are typically DC loads. So again, like I said, we're going to talk about recharging the batteries and the other components used, and then wiring. So I mentioned, up here a generator. I personally carry a small, it's actually an inverter, gasoline powered inverter. It's 2,000 watts, and that's more than enough to power the charger And that charger then is putting a 75 amp DC output, which at 12 volts would be 900 watts, but it's putting out more than that. It's putting out like 14.5, so it's doing over 1,000 watts that it's putting back. So let's say 1,000 watt hours, so 1,000 watts per hour it's putting back into the battery pack. So let's talk about some real world examples here. So say you have four 12 volt 100 amp hour. We're going to use lithium, because if you're not using lithium, you're really wasting your time and money. Lithium is so much better than lead acid, and I've got videos dedicated to that under our EV4U Custom Conversions channel. But like we mentioned on the battery one last episode, lead acid, only 50% of that stated capacity. So if you have a 100 amp hour battery, only 50 amp hours is usable. Go with lithium and get the whole 100 amp hours, plus all the other advantages I discussed. So back to our example, four 12 volt batteries at 100 amp hours each. If they're in parallel, that gives you 4,800 watt hours. Okay? Now, if you have four solar panels at 100 watts apiece, and you have two of them in series, so two sets of two in series, and then those are in parallel. And so we're going to make the assumption that we have 6 hours of sunshine per day. And so the solar output average, if it's rated at 400 watts, for the sake of calculation and discussion, we're going to say we get an average over 6 hours, because you may have clouds go by and whatever. We're going to have 6 hours where we're going to get at least 50% solar output. So using the above average, the above example, we get 200 watts times 6 hours. We're going to get 1,200 watt hours per day. So you see how we're calculating that? Now, on a good day, at the best time of year, at a great location where you've got the right angle of the dangle, so to speak, and everything's great, you may be getting 380, 390, getting closer to that 400. But if you want to design a layout and plan for the average, I recommend using a 50% figure, and then depending on where you're located, where we are, we actually get more than 6 hours. I'm using 6 hours as a little more an average in the summertime for North America. And so depending on where you are in the summertime in parts of Washington State, you're not going to get 6 hours, or on the Oregon coast, even parts of the California coast, you're not going to get 6 hours of sunshine. You may get almost no hours of sunshine. So location, location, location when it comes to solar. But anyway, you can see that you're going to have 1,200 watt hours average, approximate here, per day. So the recharge time will be based on what your battery state of charge is, how many watt hours do you need to charge, versus your solar output minus your consumption. So using my own usage as an example, we typically during the middle of the day we're not using much power. I have certain things that are on all the time. The cameras are on all the time. If we're not at the trailer, the alarm system's all the time. And these are all very minimal draw items. We may leave a fan or two on. Again, on our first episode talking about loads, we talked about how much those things draw. Those are all small draw items. But typically in the middle of the day, we have very little going on. we might use the microwave oven to heat up our lunch or something. And you're going to run that for, 4 minutes maybe for 2 people, at the most. So not a lot of loads during the middle of the day. Our loads will be first thing in the morning, cooking breakfast, taking showers, washing dishes, drying your hair, curling your hair, whatever the case would be. I don't have those loads, but my wife does. So morning, we have loads. Well, in the morning, our solar is starting to kick in, but we're probably going to be drawing more than we're going to be putting in. But that draw is going to be offset by whatever solar we are putting in. Then in the middle of the day, when the solar is at its peak, we're not going to have any load, or very little load. So the majority of that solar input will be going to charging the batteries. Then you get later in the day, the solar is going to taper off. Come evening, when the solar is about down to nothing again, that's when we have our loads again. And so we're going to have loads for, again, cooking, dishes. Although if we're someplace and we're conserving, we'll set up to where we only wash dishes once a day. Like I said, and maybe shower every other day. There's lots of ways to conserve power, but it's not just that, you're conserving water also. Our weak link, so to speak, isn't power, it's water. And even when we had our big fifth wheel, it wasn't fresh water that was our limitation. Our limitation was our gray tank. That would fill up before we'd run out of fresh water, or before the black tank would fill up. The trailer that we have now, it doesn't have a black tank because we use a dry flush toilet. And our gray tank and black tank are almost identical in size. So basically, our weak link is the gray tank. It's smaller than the fresh tank. And so that's what's going to limit us, not power. Even if there's no sunshine, we do have a generator if we needed it, but we can go about a week on our batteries if we conserve. So let's look at this other side here. Here's a diagram. These are our 100-watt solar panels. This is our solar charge controller. These are our batteries, 4 12-volt, 100-amp-hour batteries in parallel. And then here's our inverter. It's inverting DC to AC to run the AC loads. So let's look at just this example here. These are small panels. They're 100-watt panels. That's what I have on the roof of like my car trailer, on the travel trailer we just built. I have 4 on the car trailer, but I have 8 on the travel trailer. But they're just 100-watt panels, which I'd say that's the minimum you'd want as far as a size of individual panels. But they, depending on the space you have and everything, like the array on my truck bed, those are 200 watts each, and there's 8 of them for 1600 watts. But for this example, we're going to use 100 watts. And so maximum output, per panel is 100 watts. The open circuit voltage, so that's with no load on it, is 21.6 volts. Optimal operating voltage, 17.9. To charge a 12-volt battery, you need to have more than 12 volts. Most alternators, for instance, put out 14.5 to 14.6 volts. That's that potential difference in order to charge that 12-volt battery. You can't push energy in. If you're if you have 12 volts coming out of your alternator, you're not going to charge a battery, because the battery fully charges 13.2 volts. So unless the battery was at 10 volts, 12 volts going in isn't going to do you any good. And even a float charge for lead acid, it's usually at 13 0.8 volts for a float. So that's why something like this works, because you have that potential difference. Optimum operating current, 5.72 amps. Short circuit, so maximum current, 6.24 amps. Maximum system voltage, so if you have all these in series, the maximum voltage that you could run with these panels would be 600 volts. And so how many panels would that be? Well, you take the 600 and divide it by, you've got the series fuse rating. So you're going to put a 15 amp fuse on here. So those can be an inline fuse. They fit the solar connectors. The weight per panel on these particular panels, just under 14.5 pounds. And of course the dimensions. Less than 4 feet tall, under 20 inches wide, and less than 1.5 inches thick. So you have your solar panels, and in this case you can see we have them hooked up where we have 2 in parallel and then those 2 in series. Okay, can you see that? Positive, positive on that one, and then positive and negative here. So these 2 are in series, these 2 are in series, and the 4 of them are in parallel. We go through a fuse, and then we have a switch. You want to be able to switch your solar panels. And the main reason for that is your solar charge controller needs to be powered up first, which means it needs to be connected to your battery pack before you have solar input. I've never tried it myself, but I've read where people have done it incorrectly and they've damaged their solar charge controller. And so don't do that. Make sure that you connect the power to the solar charge controller from your battery pack first. Then close the switch to your solar panels. Now you want to be able to switch the power going into the solar charge controller from your battery pack also. So, I always put, as close to the battery pack as possible, so when you shut off that switch, the rest of the system is disconnected. That's the best way to do it. You can see that the 4 batteries are in parallel. All our positives are together, all our negatives. We have a switch, and then we have a fuse that goes to the inverter, and we're fused going to our solar charge controller. Fuse sizes, wire sizes are going to be based on your loads. And I can't answer the question for, what you might have, but based on your loads, that's what you can have. And you can figure that out by Ohm's law, like we talked about in a previous video. This is a 60 amp solar charge controller in this example, and I'm using that because that's what I use for, like I said, for 8 panels. That's the appropriate size. And then the inverter, your wiring size from your solar charge controller is going to be much smaller than it is going to the inverter. The inverter, based on what size inverter you have, it's going to depend on, how much current that you could possibly draw. And based on that current, that's going to determine the size of your cables, and the size of your switch, the size of your fuse, so forth. This particular one, in this example, just to give you a kind of idea, it's a 3,000 watt pure sine wave. That's 3,000 watts continuous. In my Volkswagen Doka, for instance, I don't know what this one is peak, but the Doka, for instance, it's 4,000 watts continuous, and it's 8,000 watts peak. And I forget how many seconds that is, but this is the important number, the continuous. And I don't normally draw more than, say, 2,000 watts at any one time, typically. So I've got margin. And the output is 100 to 120 volts AC. That's the output, AC output coming out of the inverter. The input is 10 to 16 volts DC going in, It's got the built-in charger with a 75 amp output. It's 85% efficient. The noise when the fans are on, it's cooling, it's less than 50 decibels. It weighs 63.5 pounds, so the inverter with the charger is pretty heavy. And of course, here are the dimensions. So another thing I want to talk about, I talked about fusing switches, your wiring. The other thing is your shunt. Now, not to get too in depth here and everything, so the shunt basically is a device that's going to be providing you with your current information. And some of these, what they call smart shunts, shunt's really dumb. It's just a known resistance, and you're measuring the voltage drop across it. But anyway, the meter's what's smart. The meter's going to be measuring the voltage of the system, and it's going to be measuring your voltage drop, that's your current flow, and then it's going to be able to figure your power and do all your other calculations, everything. But the shunt is just the required device. It has to be on the negative side of your battery pack. You don't want to put anything between the battery pack and the shunt, because if you do, that's not being measured. Whether it be an input or a load, you're not going to measure it if you put it on this side of the shunt. All your loads and all your inputs need to be on the opposite side of the shunt from your battery pack. Okay? So here, that's a quick nutshell setup of charging. So that's how that works to charge your batteries using solar. So how much do you need? Well, again, like I've said all along since the very first video, the most important part of this whole equation is calculating your loads. You need to know what your demands are on your battery pack and on your solar or your wind turbine or whatever you're generating, whatever you're going to be using to recharge the batteries. All that goes all the way back to what do you need to provide for your loads. How long you blow drying your hair every day. How much energy does it take to run any of your appliances, whether they be AC or DC. The AC ones use a little more because you're going to be using an inverter to power those. And there's a loss there. There's a 15% loss if it's only 85% efficient. So those are your greater demand loads. And like I said, in my case, my greatest load, because it runs for the longest period of time with the greatest amount of energy draw, is the water heater. And it'll run half hour to an hour a day at 14 to 1600 watts. So that's my greatest load. Now another load that's kind of a subtle one, because in the snapshot sense, it's only 120 watts. And that's my refrigerator and freezer. They're 60 watts a piece, but they run 24 hours a day, or they're plugged in 24 hours a day. And they run, my guesstimation is, they run half that amount of time, or 12 hours a day. So you're going to take that 12 hours times that 120 watts, okay, and that will give you the total for the day. And so if that was all that you were running, you'd say, I got to have that much energy in a battery pack to run my refrigerator and freezer for one day. Okay, that's your load. The battery pack part of it is, if that's what my load's going to be and I'm going to run it for one day, I would need this much battery pack. But you don't want to run it just for a day. I recommend at least a 3-day. Or if you're going camping, again, probably 3 days, time getting there, time the weekend, and time to get back. Typically a 3-day would be minimum. So you're going to take whatever that daily need is and multiply it times 3. That's the size of your battery pack. Then, how fast do you want to be able to recharge that battery pack? Well, if you got 3 days worth of energy, you got to have enough solar or other input to stay ahead of your draw. So whatever that daily draw was that we talked about first, your solar needs to exceed that so that you can provide for that draw and then have excess for your battery pack, and also excess for when the sun's not shining, so forth. So that's why I use that 50%. So anyway, in the future we can talk about any of these that you would like to discuss individually. We can do a video just on, hydro. We can do, just, talking about solar charge controllers or, solar panels. Any of these things individually, but we're just hitting the basics of the big picture. And so, just so that you have that basic understanding, because the question that everybody asks the most, if you look at social media and stuff, over and over, and the questions that we get emailed to us is, how much solar I do need, or how many batteries do I need? Well, I can't answer that question until you tell me what it is you're trying to run. What are you trying to power? That's where it all starts. Answer that question first. The first video we did in this series talks about that, how to calculate that. Once you know that, then the rest of it just falls in place. Okay? And so I'm going to do some videos in the future also. Usually when I'm on a trip, I'm focused on having fun, and I'm not, the video guy. But I'm going to try to remember to do some real-time, real-life scenarios showing what our loads are and what our input is, so you can see why I designed the system the way I did. And mine is overkill. I have the ability to charge in a good day. I can fully charge my system in one day. Okay? And so I have much more power, coming in than what I put out at any given day. That's what you ideally want. But, there's budget considerations and so forth for people. This travel trailer we did, it was easy for me because all of the battery packs, which I have 3 individual battery packs, and 2 solar setups, and they were taken from other things. I didn't purchase these just for this trailer. I actually had these things that had other uses at one time that are now repurposed for this trailer setup. So, it was an easy decision on how to do it because it wasn't a cost consideration. But when you're looking at a big picture and you're looking at space and cost, then you need to go back and look at what do I really need to power. And like I said, it's what are you powering and for how long? Bottom line. Anyway, I'd be happy to answer any questions you have. Appreciate you watching. I hope these have some value to you and that you would like and subscribe. And then hopefully we'll see you in the next one. I'd like to thank those of you who watched my entire video. Some of them are a little bit long. This one was like 34, 35 minutes. But if you made it this far, I'm going to give you a bonus video. And in the bonus video, we're going to give kind of this example of what I hear people asking the most. They're just asking for what's the bare minimum kind of thing. I just have these basic requirements. And again, I can't answer specifically because I don't know what items you're using. But I'm going to give you an example so that you get the idea for those who haven't already gotten it, okay? We're going to drive it home a little bit. So let's just say you have a refrigerator and it draws 60 watts. Remember, we want to figure our usage, our consumption, on a daily basis. So again, that compressor is not running all the time. It's going to depend on, the temperature setting you have it at, how cold, using this as a freezer or a refrigerator, what's the ambient air temperature, on and on and on. Different things will affect the things, ability to maintain a set temperature. So we're going to use the premise that that compressor runs half the time. So it runs for 20 minutes and it's off for 20 minutes, and it runs for 20 minutes, off 20 minutes, kind of thing. Okay. So we're going to figure over the course of a day it's going to run 12 hours. So 60 watts times 12 hours gives us 720 watt hours. That's how much that refrigerator is going to consume in one day. Let's say we have some lights and some fans and then electric devices, our laptop or phones or whatever we're charging and using throughout the day. And again, your items, your consumption will vary. It's all individual. But using this example, 10 watts for 3 hours, that's 30 watts. 10 watts of 6 hours, that's 60 watts. 100 watts of 4 hours, that's 400 watts. And if we add those all up, that's our total consumption for the day, is 1,200 watt hours. So we're going to need enough battery to provide that for at least that one day, and then maybe you're charging it up at night somehow with a generator or whatever. Who wants to live to a generator at night? So now we're going to talk about how we're going to do that, the battery storage. And we're going to say batteries and solar here. So one 12 volt, 100 amp hour lithium iron phosphate battery is basically 1,200 watts. It's actually, if you used every single ounce of energy in it, it's like 1320. But we'll say 1,200 watts. That's 12 volts times 100 amp hours. That's 1,200 watts. The actual nominal voltage of it is 13.2 volts. But anyway, close enough, okay? You can see that one battery would handle one day. Well, at the very minimum, I recommend that you have 2 batteries, okay? Get you through a day of whatever. And but here I just ran a scenario based on this load. It's 1 battery per day. So if you had 4 batteries, you had 4 days. 3 of them would be 3,600 watt hours or 3 days of usage. Okay? And if you're only going on a 2-day trip, bingo, you're good. You've got a little extra in case you used extra or whatever, you're set. Okay? Always better, whether it's money, solar, batteries, whatever, it's better to have it not to need it than to need it not to have it. So now we're going to go for a longer trip. We're going to be gone for a week. We got 3 days worth of batteries. What happens after 3 days? Well, we can't use our electronic devices, our refrigerator's going to stop, so forth. So we need to have a way to recharge it. You can recharge it with a charger and a generator. You could recharge it, with some of those other methods we talked about earlier in the video, or you can use solar. Now let's say with the solar, people are, how many panels do I need? Well, one 100 watt solar panel, if you got good sunshine for 6 hours a day, and we're figuring you're getting 50% of that solar panel's maximum output for 6 hours. So maybe you get sunshine for 8 hours, but part of it you're not getting 50 watts, you're only getting 20 watts. And maybe, in the late evening you're only getting 10 watts, but it averages out to 50%. So 6 hours at 50 watts would give you 300 watt hours per day. So 50 watts times 6 hours, okay? Well, that's not as much as we're consuming. It's a fourth as much as we're consuming. So if we use 4 panels, 4 100-watt solar panels, and we 6 hours a day, 50% efficiency, that would be 1,200 watts a day. That would do us. That way, if we don't get that much a day, we still have our batteries as a buffer. Okay? And this hopefully is a big enough system. We're going to be a place where we have enough sunshine, blah, 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 that we could run indefinitely, power-wise. Okay? So you see how we figure that? You can see that if you went with only 2 100-watt panels, you're going to be losing 600 watt hours per day. So if you had, 3 batteries, 3 days, you're losing half a day. You can figure out how much time you're going to have overall. So anyway, just a little bonus material here to kind of help you understand the big picture I've been trying to paint over the last 3 episodes. So, appreciate you hanging in there. Hope you enjoyed this, and we'll see you next time.